introduction. Hello, everyone. Yes, I'm very happy to revisit MSU. My last visit was actually 2009. It was a long time ago. I'm very happy to be here. I should, okay, right. Yeah. And yes, today I'd like to talk about some nuclear structure studies revealed by using knockout reactions. Here, I show a cartoon of a Japanese toy named Daruma Drop. Using this toy, we swing a hammer to aiming at hitting just one piece of this toy. And if it is successful, just that piece is going out. And then the rest of the toy doesn't feel what happens. And then after that, because of gravity, it drops. Then we have this toy with a slightly shorter, how to say, with a slightly shorter one. And actually, what is happened in the knockout reaction is very similar to this Japanese toy, as I will explain soon later. Okay, so let me start with this figure. Of course, you know that. On the left, I show the single particle structure of atomic nuclei. As you know well, motion of each nucleon inside the nucleus is mainly governed by a mean potential generated by other nucleons. As a result, we have this shell structure and also the magic numbers, right? But here, I'd like to raise a question. To what extent this single particle or independent particle picture is correct? Intensive studies so far revealed that only 60 or 70% of atomic nuclei can be understood in this picture on the left. It is because that we have many nucleon correlations that cannot be treated in the single particle picture. So there are many types of correlations, but on the right, I show some examples. That is nuclear clustering. We know that in some nuclei, alpha cluster structure exists. Also, we may consider deuteron-like pair or dineutron. These kind of correlations cannot be well included in the single particle picture. And here, okay, I think nuclear physics is very interesting, right? Depending on our viewpoint, it shows different faces. That is a typical, how to say, characteristics of nuclear physics, I think. And here, knockout reaction plays an important role. If we would like to know the single particle nature of the nucleus, we can knock out a single nucleon. Can be found. And if we are interested in this cluster structure, okay, we can knock out the cluster of interest. By that, we can see the clustering nature of atomic nuclei, which breaks the independent particle nature. Okay, this is what we are currently doing, and that should be the main content of my talk. Okay, let me start with nucleon knockout reactions. So P2P, proton-induced proton knockout reactions have been used as a spectroscopic tool for the proton single particle structure of nuclei. So here I show some, how to say, illustration of P2P. we have an incident proton. It is impinged on the target nucleus and it hits one proton and knocks it out of the nucleus. And in the final state, we have three particles, proton, and residual nucleus B. And we have 10 variables, right? Three momenta, and the mass of this reaction residue B. But we have energy and momentum conservation, so only 6 out of 10 are independent. So for example, if we measure the momentum of 2 outgoing protons, kinematics are completely fixed. So this is called kinematically complete measurement. And here we assume the impulse approximation, as in the Dharma drop. Okay, so we assume that proton just hit one proton and not disturb the motion of the reaction residue, particle B. And this is something like the situation that the two objects are connected by a spring. So it moves like this. In the initial state, the target nucleus is at rest, of course. So in total, momentum is 0. So two objects move like this. And suddenly one proton is knocked out. And if the motion of this particle B is not disturbed, it keeps its motion. And if the picture is correct, we can relate this momentum B and the nucleon proton momentum before the collision. So if we think that, we may say measuring knockout reaction will be taking a snapshot of the proton momentum distribution in atomic nuclei. And on the right bottom, I show some examples of experimental data taken at RCNP, Osaka University. And the observable is a triple differential cross-section here. And variables are taken to be the energy of proton 1, solid angle of proton 1, and solid angle of proton 2. And in this measurement, K1 was fixed. And we imposed a coplanar condition and just vary the scattering angle or polar angle of this particle 2. Okay, so the cross-section is plotted as a function of theta 2. But what we actually would like to vary is KB, this recoil momentum. Okay, this PB is almost the same as this KB. Okay, so this cross-section can be interpreted as a function of this recoil momentum as shown here. Okay, and you notice that with a very small value of recoil momentum, a cross-section can be a dip or a peak. This is very simply understood. Classical mechanics tells us that the L equals R cross P, right? And if P is 0, we cannot have a finite value of orbital angular momentum. So if cross-section has a dip at the very recoilless position, we can see that it is a non-S orbit. And if it has a peak, we know that it corresponds to the S wave or orbit proton. And actually, the blue dashed curves show the result calculated in the plane wave limit that can be understood as the absolute square of the momentum distribution. You can see a good correspondence between the curve and the experimental data, right? But some of you are concerned by the difference remains, but that is because of the missing of distortion. for incoming proton and outgoing protons. And using the distorted wave impulse approximation, we can take into account the distortion effect. And by that, we obtain this red curve that perfectly explain the shape of the cross section. So I would say the distortion effect is under control. Maybe Philomena has a different opinion. Uncertainty quantification will be necessary, but let me say, at this moment, so distortion effect will be under well control. Okay. So far, I have mentioned only the shape of the cross section, but also important is the height, magnitude of the cross section. By that, we can extract the spectroscopic factor, the measure of the single particle structure. And in the paper, in this paper, Noro and collaborators reanalyzed the P2P data taken at RCNP at 400 MeV and compared the spectroscopic factor and the spectroscopic factor deduced from EE'P, electron-induced knockout reaction. That is believed to be the cleanest probe for the single particle structure. And here they show the ratio of the two spectroscopic factors. If it is unity, they are consistent. And you can see that although there are some deviation, but for this carbon 12, oxygen 60, and calcium 40, for the levels near the Fermi surface, the two spectroscopic factors are consistent within uncertainty of 15 to 20%. This is nice, I would say. Okay, please.
What is the light blue, the bars, the light blue bars? What?
Light blue bar is correspond to the uncertainty of the EE'P spectroscopic factor. Sorry, I should have mentioned that. Thank you.
So the error bars on the red are only coming from the P2P data.
Right.
Okay.
And there are two types of data results are plotted. One corresponds to the using the Dirac phenomenology optical potential. The other one for the kind of microscopic folding model. So by the difference between these two, we may see how the optical potential is uncertain. Okay, anyway, but I would say the two spectroscopic factors are consistent. If we can say so, it will be nice because P2P can be used, proton can hit also neutron rather easily, right? So PPN can be done. And also, it can be applied to the physics of unstable nuclei because we can use the proton or hydrogen target. Okay, so luckily, I had a chance to collaborate with many experimentalists. At that time, there were a series of experiments at the RIBF RICAN, and they studied the mainly neutron-rich nuclei for their single particle structure and the magic numbers. And these are the fruit of such collaborations. I'm very happy to join such large, big collaborations on the physics of unstable nuclei. And of course, I cannot explain one by one here, but as a highlight, as Grigor shows, I'd like to show this by the experiment led by Ryo Taniuchi and collaborators. We found that the Nucleus 78 is a doubly magic nucleus. Whether it is doubly magic or not has been a long-standing question since the RIBF was launched, actually. So I'm very happy to join as a collaborator to conclude such an important question. Okay, that's it. So in the studies I just showed the references, we specify the spin parities of the low-lying states of neutron-rich nuclei. And in that study, the key quantity, key observable is the momentum distribution of this reaction residue, B. As I mentioned in the beginning, this KB can be related to the nuclear momentum distribution. And by that, we can pin down the spin parity or the orbit of the knocked out proton or neutron. Here I show just an example. This is calcium 54 ppn to calcium 53 going to the ground state. And depending on L, angular momentum, orbital angular momentum, the momentum distribution has a different shape. And we tried some values of L, and we concluded that in this case, L could be 1. And by that, we can specify the spin parity, and that is also done for many other states. But here, I would like to point out that, okay, this momentum distribution is very good, but as I said, there are 6 independent variables. But in this case, only this KB and MB were specified, right? So in that sense, this is a kind of inclusive measurement, not kinematically complete measurement. So 2 out of 6 degrees of freedom of K1 to K2 are integrated out. So maybe we can consider what is the most exclusive and ideal observable in inverse kinematics. In normal kinematics, as I showed, the TDX, triple differential cross-section, is a very good observable. But if we calculate the triple differential cross-section in inverse kinematics, here I show the carbon 12 P2P going to the ground state of boron 11 cross-section. You can see that very, how to say, peculiar shape of the cross-section. This is plotted as a function of theta 2. And in some region, you have 2 values of the cross-section. That means there are 2 solutions of the kinematics. And it is not easy to see from the figure, but at some theta 2, cross-section diverges. This means that choosing these variables is not good in inverse kinematics. The reason is quite simple. This is a result of the classical mechanics, actually. And okay, here I show the correspondence between E2 and theta 2 in normal and inverse kinematics. In normal kinematics, one value of theta 2 corresponds to one value of E2. So choosing this as a variable is good. But in inverse kinematics, that is not the case. So there are 2 solutions. And when the solution has a double root, I can show that the cross-section diverges, actually. So this clearly shows that in inverse kinematics, you should choose E2, not theta 2, as an independent variable. By that, we can define the four-droplet differential cross-section as a function of E1, omega 1, E2, and phi 2. Phi is the azimuthal angle of the second proton. Okay, so in this case, cross-section has a 2-peak structure. Okay, now we consider P2P from carbon 12, considering the knockout P wave. So cross-section should have 2 peaks. And QDX shows that nature. So the correspondence between the observable and the momentum distribution is much clearer when we use the QDX than using TDX. So in inverse kinematics measurement, we should measure QDX for the completely, how to say, exclusive observable. Here, I would like to give a small advertisement of a new numerical code named PICOE, PIKOE. Some people call it PICOE, but PICO is our intention. But anyway, in this code, with this code, you can easily calculate the proton-induced nucleon knockout reactions in both normal and inverse kinematics. And and I hope that the experimentalists use, of course, theorists can use this code to calculate the knockout observables. Okay, so far I explained the nuclear knockout. And let me back to the slide on the second slide. And on the right, I mentioned that if we would like to see the cluster structure, we should knock out clusters. So, and alpha knockout is the first example of the cluster knockout studies. Okay, this is a slogan of our collaboration, knock it out. Then we see something. And in this experiment, they measured, Junki Tanaka and Zaihon Yang did a very important role. And they and the collaborators measure the Phi alpha from thin isotopes to see whether alpha exists or not in the thin isotopes. And before that, actually, there was a very important prediction by Stefan Tupel that in thin isotopes, we may have an alpha cluster. And the existence probability depends on the neutron number. And this is a kind of proof of such prediction. And when they measure the PP alpha, they obtained a very good signal of the alpha particle from thin, in this case, thin 112, and also from other thin isotopes. So this is surprising, I would say, because for such medium heavy nuclei, the nuclear structure are mainly explained by the independent particle picture. So nuclear correlation should be there, but probably not many people expect that the alpha is inside such a thin isotopes. But the experiments showed that that is not correct. So I would say more than 100 years after the identification of alpha by Radford, alpha particles inside the nuclei were directly observed for the first time at RCNP Osaka University.
Excuse me, the question.
Sure.
So do you have a sense of what is the probability for you to see that, like alpha and the rest of the nucleus configured? What is the probability for seeing that?
Probability?
Yeah.
You're asking the number?
Yeah.
Sorry, I don't have the exact number.
So you have a nucleus and it fluctuate to a alpha plus a residual nucleus. So what is the chance of seeing that?
It's not high, I would say. But sorry, I should remember, but I don't remember that. After my talk, I can tell you the number. It is not very large, but yeah, for example, neon 20, it is something 0.3 or something. But in this case, that is lower than that value. Probably by one order, I think, but let me check the number. Yes.
So this is, I'm guessing, quite a challenging experiment because it's in picobarns. Usually we have things in millibarns. So
Yes. But yeah.
It's stable beam. Okay.
Yes, this is stable beam in normal kinematics. Yes. Okay. So
So you couldn't do this at 10:30.
okay, let me continue. For the description of PP alpha by theory, it is not difficult at all, I would say. This is very, very similar to P2P because alpha is very tightly bound nucleus, right? So we can safely treat it is a, how to say, just a point particle. But of course, in description of the PP alpha, we need alpha scattering wave function and alpha optical potential. Also, as an elementary process, we should have a proton alpha elastic cross sections. But once they are implemented, everything is the same as in the P2P description. And in this paper, we collaborated with the structure people who are doing AMD, unsymmetrized molecular dynamics calculations. And they calculated alpha distribution or alpha overlap inside the neon 20. And this is the result. And we implemented this in our reaction calculation. And without tuning anything on this structure wave function, we have this cross section that perfectly agree with experimental data, I would say. So this is very successful, I think, to show that alpha knockout can be a good probe for the alpha cluster in the nucleus. And in this case, the spectroscopic factor is something 0.3. Okay.
Do you have a sense to which the tail of the distribution dominates this, to which the ANC is the relevant quantity?
Yeah, that is a good point. But actually, what is observed is this region, peak region, not only the tail region.
Yeah.
So ANC is important, but that is not the whole story.
So, but there's a certain radius. There's like an inner radius you can go up to in these. You would say.
You mean yes. So the nuclear interior is not important in this case. But I'm thinking whether we can determine the ANC by choosing the incident energy, for example. If we reduce the incident energy, maybe the cross-section is governed by only the ANC. If that is the case, we can use this PP alpha to as a tool to determine the ANC. Okay, thank you. Okay, so this is a collaboration with Grigor, and I'm very happy to join this collaboration. And very recently, they provided the ab initio single particle alpha wave function shown here. And again, we used this in the knockout calculation, and the result is shown on the right. It is very successful, I would say. So yeah, we know that the ab initio wave function is consistent with the reaction observable in this case. So this is very important thing, I think. And but this is not the end of the story of PP alpha. So this is our trial on the titanium 48 PP alpha going to calcium 44. And again, we use AMD calculation. Okay, the figure is a very busy, so let me just explain quickly. Please just look at that dashed line on the right. This is a result of AMD. It is a written mean field, but it is essentially same as that of AMD. And so this cross section is very far away from the experimental data. So alpha amplitude cannot be described well by AMD calculation. So I'm very curious what happened if we use the ab initio calculation, and I hope the collaboration will go on. Okay, this is the situation. And okay, this is the observation of alpha clustering of neutron-rich nucleus, beryllium-10, in inverse kinematics. And we showed that the cross-section, this is a triple differential cross-section. Okay, we tried two structure model. One is AMD, the other one is THSR. This is a Tosaki-Horiji-Shuk-Lepke model. It's a cluster model. And we changed the height by, how to say, 10% or something like that. But with only such a tuning, we got a very good agreement with experimental data. So this will be the direct observation of alpha particle inside the ground state of this beryllium-10 nucleus. If we artificially change the wave function corresponding to the shell model-like structure or dilute gas-like structure, the cross-section changes in this way, and that cannot be explained the experimental data. So TDX is very sensitive to the alpha cluster structure. Question? Maybe you can say, you can ask why you use TDX, not QDX. The reason is simple, because I was stupid. When we prepared this result, I didn't realize that how the TDX is problematic. And after that, after this paper, I asked Penji to calculate, to compare our QDX with experimental data. I'm not going to the detail, but it has a one peak structure, right? In this case, alpha is in the S-wave orbit. So cross-section should have one peak. I mean, the momentum distribution should have one peak, and this cross-section shows that nature. So this shows clearly that QDX should be used than TDX. I regret actually this. Okay, so the PP alpha measurement on thin isotopes triggered quite a big project named Onokoro. And maybe some of you are not interested, but let me explain what the Onokoro is. This is a Japanese myth. Okay, we had two gods, Izanami and Izanaki. Okay, there was no Japanese island in that period. They put a spear on the chaotic sea and stirred. Then flew up the spear, and from that drop of from the spear, the first island of Japan was, how to say, generated. That is what the myth says. I don't know whether it is correct. But yeah, when we write this Onokoro by kanji, it is something like this. This means self-clustering. So Uesaka-san loves this word very much, so he named this project with Onokoro. And we got quite a big kakenhi for this project, and he is a PI, and I'm a co-PI who is responsible for theoretical description of the reaction part. And the main question is, how many alpha, triton, deuteron, or helium-3, etc. exist in nuclei in the wide mass region? So that is a goal. Okay, alpha, as I said, it can be knocked out rather easily. Triton may be okay, but deuteron, is it okay? You say no. So can we knock the deuteron out? So, but okay, that was the big question before this project was launched. Okay, let me mention PP. So let me start with an experimental part. Because, okay, anyway, yeah. In these papers, Samantha and collaborators show the results of proton knockout and deuteron knockout cross sections from oxygen-16 at the same energy, 101.3 MeV. And you can see that the magnitude of the cross section are not very different, right? The ratio of the at the peak is only factor of 2 or 3, right? So I think this is extremely larger than what we naively imagine, right? So this may suggest that there are many deuterons in oxygen 16 than what we expect. This is an experimental fact. So probably you can believe this, even if you don't believe theory, right? But okay, yes. So this is a starting point that we considered PPD. But here, a question arises. So, okay, we can measure PPD and the deuteron can be detected, but deuteron is very fragile. So the measured deuteron may not have been a deuteron before the collision, before the scattering or before the collision. So to relate the PPD cross-section and deuteron existence in the nucleus, we should treat these degrees of freedom. Okay, that is different from our description of PP alpha. Here, CDCC appears. So I think all of you know what CDCC is, right? CDCC is a reaction model that has been highly successful in describing the breakup process of weakly bound nuclei. And here I show a schematic illustration of deuteron scattering on the target. And by the interaction with this target, deuteron can change its internal state. I mean, it can easily broken up. And the wave function can be given as a superposition of the different deuteron or PN states. If we select the deuteron ground state in the final state, we can calculate the deuteron elastic scattering. If we choose a broken up state, we can calculate the breakup cross section, right? And here, let us take the time reversal. Okay, time reversal. Then this is nothing but we need as shown in the previous slide. Okay, so taking the time reversal is very trivial thing. So if we have a CDCC wave function, we can implement it in the knockout calculation. This is how we treat the PPD cross section. So this is a reaction path that we should treat. So okay, here I impose the condition that in the end, deuteron is detected. That corresponds to the experimental condition. And in the scattering of this reaction residue, deuteron can change its state. So we should consider this reformation process in the final state due to the final state interaction. And also, this proton can hit deuteron and also PN pair. If this proton hits this PN pair, it can go to this PPD channel. So all of these things should be treated. But unfortunately, currently, we don't have a good wave function of deuteron and PN pair in the nucleus. So I hope some ab initio calculation can do that. But currently, that is not possible. So we have to concentrate on this reaction parts, starting with deuteron. Okay, this is a big assumption, but let me assume that deuteron exists in the nucleus and proton hits this. But as a reaction theorist, we can treat this path. The reformation process and see what happens on the PPD cross section. And okay, by the way, we give this framework name CDCCIA. This is a combination of CDCC and DWIA. It is published by Chazono and collaborators, including me. Okay, these are the examples of PPD at 250 MeV. And on the left, I show the oxygen 60, oxygen 60 PPD. On the right, nickel 56 PPD. Oh, sorry, the figure is rather busy, but let's see just red and blue dashed one. Red solid curve is the result of CDCCIA, and this blue dashed is DWIA. So the reformation process changes the cross section in this way. The difference is not very significant, but appreciable, I would say. So I think the reformation process is important. But we should not, how to say, be careful about the, how I can say, the interference between these two reaction paths. This is a DWIA-like path, and this is a reformation path. And if we take just the reformation path, the cross-section is very, very small. So this difference comes from the interference between these two reaction paths. And interestingly, the interference can be destructive or constructive. So that we don't know the reason currently. So we are now studying the mechanism of the, how to say, behavior of interference. And okay, so CDCCIA can be applied to is not sorry. Thank you. CDCCIA can be applied to dineutron knockout or diproton knockout reactions. And in this case, we should treat these reaction paths. That is more complicated, but still tractable, I think. And in the end, we don't have a ground state of this two neutron pair. We should measure both neutrons and measure the distribution of the cross-section regarding the relative momentum. That should be the observable that we should discuss. And this study is ongoing, and hopefully we report something in near future. Okay, this is a summary. I have overviewed recent nuclear and cluster knockout reaction studies for revealing the two phases of nuclei, that is a single particle structure and a nuclear clustering. For PPN, it is important to recognize that P2P can be an alternative to E prime P for single particle studies, and that can be applied to neutron knockout and also knockout of neutron-rich or proton-rich unstable nuclei. And in future, probably many measurements will be done in inverse kinematics. And in that case, for the exclusive quantity, we should use QDX, not TDX. For PP alpha, the existence of alpha in the ground state of a nuclei are being established, but the theoretical description is successful only a very limited case. So we should make it more systematic with the help of nuclear structure people. For PPD, we should treat the fragileness of deuteron, and CDCCIA can be used for that purpose. And for other things, okay, I have not shown, but we have some calculation and observation of triton and helium-3 knockout reactions, and the result will be soon appeared. And also CDCCIA is going to be applied to dineutron knockout reactions. Okay, that's it. Thank you very much.
Are there any questions from the audience? Kyle.
Thank you for a really interesting talk. So I guess one question would be, so the matrix element in DWIA that causes this knockout is the T matrix element between the projectile and the cluster or the nucleon that is knocked out. And from my understanding, oftentimes this is taken to be a free matrix element. We ignore the in medium effects of the rest of the target. and we could factorize it out. To what degree, like, do you have a sense for what systems that's valid and what systems that's not valid? And could that explain the issue with titanium-48?
Okay, basically it depends on the reaction region. When we knock out a particle from very nuclear interior part, the immediate modification should be necessary. But at the same time, the distortion or absorption effect becomes large. So such component would not be, appear in the end. So basically we knock out the particle from the nuclear surface. So in that region, in that case, probably using the free nuclear interaction would be justified. But there is an attempt to include the immediate modification in this proton-proton reaction part. So we can compare the results changing the target systems.
Would it be possible to develop an in-medium force for a cluster knockout?
Cluster knockout, that is a good question. So, yeah, that is a good question. Now, let me see. If we, okay, for proton alpha scattering, in our case, we use proton nucleon free effective interaction. But if we use proton nucleon G matrix interaction, for example, in that calculation, maybe we can take into account the medium effect.
Did you have a?
I did. I wrote it down. 1 second. For slide 7.
So,
Yeah, for the graph right there, it's cross section by momentum, correct? Divided by it's differential cross section divided by momentum. What is I'm confused with the units on the y-axis.
this one?
Y-axis, the other one.
Oh, yeah, okay.
Yeah, so it's cross section by momentum, or is that right?
Okay, I should have explained that, but this is a parallel momentum. So,
Okay.
it's okay?
No, okay. Yeah. Very good. Very good.
It is cross-section over momentum.
Okay.
The same way like a differential cross-section.
Exactly.
Okay.
Reverse gradients.
Thank you. Yeah. Okay. Yep.
Wilhelmina?
So as you are well aware, there's some controversy about the spectroscopic factors obtained from knockout on heavier targets versus the proton knockout. And so your calibration of the proton knockout on E prime P is really nice work, right? You're showing this overall consistency. But then there's that statement there that says that for the lead, there's significant discrepancy found. So, and I see this, perhaps the uncertainties aren't fully quantified, but there's a significant deviation from those values. So how is this understood?
I have no idea. Actually, currently, this is a big open question, I would say. If I know the answer, I should have explained that. So this is a big.
So it's just a puzzle.
Yes.
So
Exactly.
are there other isotopes between calcium and lead that one could study?
For zirconium, probably we have a similar deviation as in lead-208. So if the target nucleus is heavy, that corresponds to probably the strong distortion effect, something happens. That is phenomenological observation. But yeah, I would like to understand the reason, but currently I have no idea.
Thank you.
Chair?
Yes.
Probably.
Remco?
So I have a very simple question, but recently I learned people wanted to study helium-6 knockout. And this,
Sorry.
maybe you know. And that kind of put the whole thing in sort of a different perspective for me, because the interpretation of this cluster knockout is a little odd, right? You can make any reaction and you can produce any system. You can make helium-6, you can knock out almost anything, but the interpretation is not necessarily that there is a cluster inside the nucleus. And when people were talking about helium-6 knockout, I'm thinking, okay, it's not very likely that there's a helium-6 inside whatever nucleus they're looking at. So is the interpretation of having a cluster, is that the only way to explain this? That is, and if you do fragmentation, when we make rare isotopes, we produce anything from shooting a nucleus at something light. I don't think we interpret that as being a cluster inside the nucleus. So what is the...
But that is very much related to our subject for PPP, right?
Mm-hmm. Yeah. it's
Even
related.
if we have a deuteron, that does not necessarily mean that deuteron was in the nucleus, right?
Mhm.
But if we include all of these things, we can relate the cross section and the initial wave function, right? In this way, to what extent this should exist can be discussed. That is what I think. And that will be also the case for helium-6 knockout.
But isn't this true for alpha particle as well?
Alpha particle as well, but for alpha particle, we have a strong condition on the detection phase, right? So question is, what is the wave function starting with that condition? So it depends on the rigidness of the particle. And for alpha, I think it does not change its internal state during this final state interaction. And also, it cannot be easily broken up by incident proton. If so, we can, select the component of the free alpha particle in the nucleus.
Yeah, well, it's interesting. I'm still a little confused. The whole idea, if you do any reaction on a nucleus, like take the tin, and there's an alpha cluster in there, that's a significant component. Any reaction that you would do on that nucleus would contain a component which is the reaction on the alpha cluster. Yet I don't think we see any evidence of that if we do some reaction.
Yes.
So this sort of dual picture is a bit confusing to me.
Oh, really?
Yeah.
Maybe we can discuss.
Yes.
Daniel,
So I'll ask my question in a funny way. So when you play this Japanese toy,
Mhm.
what's the probability that the Japanese toy stays in one piece after each strike?
Mhm.
In other words, the Japanese toy could be destroyed after you strike it, right? So in your model, you assume that the nucleus, a B, stays in one piece every time, right?
Yes.
So, but that might not be the case. Like the Japanese toy, it might all fall apart if there's excitation.
Excitation. You
This
are
nucleus.
talking about the impulse picture. I mean that the hammer can disturb the other part.
Right.
Okay. Yeah, that is a question. Okay. So for that is related to the validity of the impulse approximation. So for that, sorry, I should. There are some benchmark. Yes. Okay. Yes. Fadef people calculated the knockout cross section and compared with DWIA in their terminology, and they found that the difference is very small. Of course, Fadef calculation does not assume the impulse approximation, so this shows validity of the impulse picture. Of course, it depends on energy. Okay, on the left, I should 400 MeV per nucleon, and on the right, 100 MeV. This is a work by Raquel Crespo and collaborators. Also, we did some benchmark calculation with transfer to the continuum model by Sevilla people, Antonio Moro, Mario Gomez Ramos. And we found a good agreement between our DWIA in their model. Of course, their model does not assume the impulse approximation. By that, we can see to what extent the impulse picture is valid.
Chloe, then Kyle.
Yeah, I had a question about the PPD calculation with CDCCIA, I guess. So the operator in the T matrix, is it a proton-neutron interaction?
No, it is a proton-proton plus neutron, proton-neutron interaction.
Ah, okay, okay. This was my question. Thank you.
That's the point. Okay.
I think this is related to the interpretation of the results as there being a preformation of a cluster of some kind inside of a nucleus. So in the missing mass spectrum for the alpha knockout from tin, there's these two peaks. Could you maybe explain in more detail what the interpretation of, like, there's this sort of narrow peak and then there's this sort of broad continuum contribution?
I think you're talking about this part.
Yeah, yeah. What are these two peaks correspond to? Well, there's this one peak and sort of this broad continuum.
Definitely, this corresponds to the ground state of cadmium 108, but currently we don't have a clear interpretation of this part. Yeah, it contains a quite large number of energy, excitation energy. So if the resolution is super fine, okay, this is RCNP experiment, so resolution should be good, but still it is difficult to separate. But eventually, ultimately, we should have a peak corresponding to the excited states of cadmium isotopes. I think if we measure that, yeah, that will be interesting in a way that I have not explained.
Okay, we're almost on top of the hour. So is there a final question? If not, let's thank the speaker again.